Yesterday we were working on elevator questions and things like that. Force is obviously a vector quantity. We did some vector sum of all forces. Now we're going to really do vector sum of all forces. I want you to write this question down and give it a try. It's really going to involve vectors. Okay? Involving like the vector addition from the first unit in order to get our net force. Okay, give you a little bit of time to get this one done, okay, and then we'll walk through it together. Okay, let's maybe quickly have a look at the first two things we have to do here, which is draw the free body diagram and then the vector diagram. Okay, so it's on a level frictionless floor. Okay, there's two forces that are acting on it. So I got my box, okay, and it's 50 kilograms. Force number one is directed 35 degrees north of east. So here's east, okay? 35 degrees north of east, probably looks something like that. And it is 150 newtons. Okay, and then force number two is directed 10 degrees south of east. So, and it's only 115 newtons. Okay, so those are the only two forces acting on the box. Agreed? Okay, that's my free body diagram. Nice. Doesn't help me do anything other than identify the two forces that are acting on the box. Now, I've got to take those two forces and I've got to put them tail to head. I'm being incredibly lazy by doing what I just did. Okay? So, I've now got my two forces. That kind of makes sense. That's the direction this box should go, given those two forces. Okay, it's going to be mostly east and a little bit north. Right, so that's going to be theta, this will be x, this will be y, and this will be F net. Okay, so we'll call this x2, y2, this will be x1, and this will be y1 here.
On a test, do we have to draw both the free body diagram and the vector diagram for full marks?
If you get the answer right, no. If you don't get the answer right and you don't have a free body diagram, I have nothing to give you a mark for. So in that way, take the 10 seconds it takes to draw the free body. I wouldn't even make you do the like angles, just like draw two forces coming out of the same side that are slightly angled, and it's good, right? All I'm looking at is for the free body diagram to identify your forces.
Why can't you just add the two forces?
Because if I just add them, then I'm saying they were collinear, right? And they were pulling exactly the same direction, and they're not. If I just did that, then I don't know which direction to say the net force is going in, as it's a vector quantity. Yeah? Okay, give you a little bit more time there, guys. So obviously I've got to do all the vector component stuff. Okay, so I've got to find x1. That'll be the cos of 35 times 150. Okay, so 122.87. And that'll be newtons, and it'll be east. Okay, and then y1 will be the sine of 35 times 150. So 86.04 newtons. And that'll be north. And then I got to find x2. x2 is going to be the cos of 10 times 115. Okay, so 113.25 newtons east. And y2 will be the sine of 10 times 115. Alright, so 19.97 newtons. And that'll be south. Okay, so now I've got all my x's and all my y's. So now I can calculate my resultants x. They're both east, so I just have to add them together. So that'll be the 122 and the 113. Okay, so 236.13 newtons east, and then y, they're opposite. One's north and one's south. So the 86 is the north, the 19 is the south. All right, so we're looking at 66.07 newtons north. Okay, so now I got my big triangle. Now I can find F net, or at least the magnitude of F net, using Pythagorean theorem. So 236 squared plus 66 squared. Whoops, I don't want that. Oh no.
Second long.
Thanks. I never actually go in there. Okay. I never use that for anything. All right, second square root. That's what I want. Okay, so I'm going to take my 236 squared plus the 66 squared. All right, so my net force is 245.19 newtons. Okay. I also need the vector, because force and acceleration are both vector quantities, and they always have the same vector. So tan to the minus 1 of the opposite side, the 66, over the 236. All right, so we're looking at 15 degrees, 15.6 degrees. Okay, and that'll be north of east. All right, I got my net force. What am I supposed to find? I'm supposed to find the acceleration. How do I find that? F equals m times a. Did I just do everything we've done in every other question? Vector sum of all forces, m times a. It's always the same two things. It's just how you get the vector sum that's tricky. Okay, so last step, acceleration is F net divided by mass. So we have our 245.19 divided by the mass, which was 50. Okay, so the acceleration is going to be, and I think we only have two significant digits, right? Yeah, the 50 only has two, and so is the 35. So 4.9 meters per second squared at 16 degrees north of east. And of course, I would also accept 74 degrees east of north, as those are both the same direction. Okay, so that used a fair amount of stuff from last unit. Okay, vector components, still part of this unit. Acceleration formulas, still part of this unit. Okay, we're still going to have to do those things from last unit. Okay, all right, questions on how that one worked? We haven't talked about inclined planes yet. Let's talk about inclined planes before we talk about systems. All right, I want you to copy this one down. Probably doesn't seem like it gives us very much information. It's a ramp with a box on it. And we're supposed to calculate the acceleration of the box, given only the mass of the box and the angle of the ramp. Why do things go down ramps? Okay, gravity. You're partly right. Partly gravity. If it was just gravity, though, which way does gravity pull? Straight down.
So the reason why it slides down is because gravity is pulling it down, but the ramp is pushing it this way. The forces cancel, it goes that way.
Yeah, it's a vector sum thing again. Okay? It's a vector sum of all forces thing. The vector sum of gravity and the force of the ramp add up to down the ramp, always. Okay? So the forces that are involved in an inclined plane are always the force of gravity and the force of the ramp. Now, which way does the ramp push? Straight out from the ramp. That's the only thing any surface can ever do. Okay, that force we talked about, the normal force, the reactive force, that can only ever be perpendicular to the surface. Okay, so when this ramp is angled at 30 degrees, the normal force pushes out this way. So if I'm drawing a free body diagram, yeah, I got gravity going this way, I'd have normal force going that way, and then if there was friction, which way would friction be going? Yeah, up the ramp. It always opposes the motion. So if I just set this thing on the ramp, friction's acting up the ramp. Okay, what if I'm pulling it up the ramp? Then friction acts down the ramp. Friction always works against you. Okay, so I would also have then obviously friction going up the ramp as part of my free body diagram. But this is a frictionless ramp, so I don't have that. Okay. So if I put something on a ramp, it wants to slide down the ramp. And the reason for that is this force, if I draw this as a vector diagram, goes there, tail to head. All right, well, if I just drew these things tail to head, it means my resultant goes right there. Whoa, I drew that good. Parallel to the ramp. Okay, right? Points straight down the ramp. Because I magically managed to get those two things about right in terms of their ratios. Okay, so we call this force F parallel. Because it's the component of gravity that acts parallel to the plane. They are parallel to the ramp. Okay, if this angle here is 30 degrees, what's that angle? 30 degrees, yep, they're always the same. This little triangle that we just drew, this vector diagram that we just drew, is always the same on every inclined plane. Okay? Gravity points straight down and is the hypotenuse of that little triangle. Normal force always points perpendicular to the ramp. Okay? And we join them just like we did here. The resultant is what the box does, down the ramp. Okay? Now, what if there was friction? We just said friction would act which way? Up the ramp. Well, then if I did a vector diagram, I just put friction here on the head of the F parallel and go back up, and then my resultant would just be this little piece here. We don't ever really draw it that way. Okay? Once I figure out F parallel, what I do is I transfer it here. Because all this box is going to do is move up the ramp or down the ramp. That's all that box can do. It's not going to fly off the ramp or fall through the ramp or do anything else crazy. Okay? Those are the only two things that it can do. Since this ramp is frictionless, I've just found the vector sum of all forces. F parallel is my net force. Now, can I figure out what it is? Yes. Okay? Because force of gravity is mass times 9.81. So this side is 98.1 newtons. How am I going to calculate this side if I know the hypotenuse and that angle? sine of 30 times 98.1, this is going to be 49.05 newtons. Can I calculate the acceleration of the box? That's my net force. Okay, so acceleration just equals F net over m, 49.05 over 10, is 4.905. Well, actually, we'd only have two significant digits, 4.9 meters per second squared down the ramp. Luke, question?
Why is force of gravity 98.1?
Because I multiplied it by 10.
Okay.
I found the force, not the acceleration. Yeah. Okay. Everybody follow what I did there? People get like thrown by inclined planes, but there's not really a reason for it. They're just like any other forces of vector quantity type of question. And it's always the same forces. They always set up the same way. The force of the ramp, okay, the force of gravity produces a movement or a force down the ramp. Okay? That's what you're working against if you're pulling something up a ramp. Is that force always less than the object's weight? Yes. This is why the ramp is the simplest machine. Okay? The inclined plane is a simple machine because it is a force multiplier. It means that I can move masses up the ramp that I couldn't lift myself. That's the whole reason we use ramps. Okay? They make work easier. They don't make less work. It takes the same amount of energy to lift something to the top of this ramp as it does to drag it to the top of the ramp. Okay? It takes the same amount of energy. But it's easier. I could actually accomplish it, okay, versus having to pick up something really, really heavy and lift it to the top of the ramp. Okay? Because then I have to exert a force equal to its weight. Maybe the thing is too heavy. Right? It's 10 kilograms. I'm too old. I probably can't lift that. Okay? That's like 22 pounds. There's no way. Okay? So, but if I was dragging it up the ramp, it'd be a lot easier. Everybody all right with that? Okay? It's also why stuff doesn't go down a ramp right away. In the real world, okay, things don't start to slide right away because of, right? So if I've got the ramp and it's not a ramp, okay, I'm not going to use the wheels on this, okay? And I've got it like this, friction is equal to the force parallel. So the cart doesn't move, okay? The more I tilt this, okay, the bigger force parallel gets, okay? Until it gets to here, and then force parallel is equal to what? Gravity, because now it's not a ramp anymore, now it's falling. Okay? So if I have it here, okay, force parallel is less than gravity, and once this thing starts to slide, it means that now friction is no longer equal to the force parallel. Okay? The moment they're equal is the moment before it starts to slide. Okay? The next degree up, F parallel is a little bigger than friction, and it starts to accelerate down the ramp. Yeah? So all inclined planes physics. Okay. All inclined planes work the same way. Okay? That's the nice thing about inclined planes. Once you figure out how to do one, you know how to do them all. The only thing I can throw in there is, you're dragging it up the ramp and friction is acting down the ramp, or it's sliding down the ramp, but the ramp has lots of friction, and you have to add force, and you got to put friction in your free body diagram. It's part of your vector sum of all forces. That's the only thing that can really make those more complex. Or I put a pulley at the top and hang a mass over the end. We haven't talked about pulleys yet, so I'm not going to do that to you yet. Okay? But we will get there. All right, everybody okay with how that works? Okay. That's what we just did. All right, this one's got two things in it that we haven't encountered yet. It's still an inclined plane, okay? So, but it's a 340 Newton box. What do I normally give you? I usually give you kilograms because that's giving me the mass. I just told you it's 340 newtons. What did they just tell you? Its weight, exactly. Sometimes a question is going to do that. Instead of giving you the mass, it'll give you the weight, which is the force of gravity. So that 340 newtons is whatever the mass is times 9.81. So could you find the mass? Okay. All right. Give that one a try. Okay. I'll draw the diagram and the setup here in a few minutes once you've had a chance to try it. Okay, so let's just get the diagram kind of set up here. So we have this box being pushed up the incline. Right, we know the incline's 30 degrees. We know the box weighs 340 newtons. Okay, so what's its mass? 34.65 kilograms. Okay, so we've got its mass, okay, and we know it's being pushed up. So there's an applied force acting up the ramp, and they tell us what it is. It's 200 newtons. Okay. They also tell us that friction is acting, and which way is it going to act? Down the ramp. Okay. That's the force we're being asked to find. Okay. The other forces are obviously normal force, okay, and gravity. Now, what are normal force and gravity always going to add up to? Nope. What's the special force when I put them tail to head that they add up to? F parallel. Okay. When I do the vector sum of these forces, right, I do that, and to see that time I didn't do a good job of it, and it's supposed to be parallel, okay, that line that connects those two, they always end up making that resultant force that's parallel, okay, to the plane. So this angle's 30 degrees, this side's F parallel. That force goes here. Okay, so there's F parallel acting down the ramp. That's the component of gravity and the ramp. Okay? Friction acting down the ramp, and the pulling force acting up the ramp. Okay? Can I calculate F parallel right now? I can, because it's part of this triangle. I know the hypotenuse of this triangle, and I know the angle in this triangle. Okay? So I'm going to take 340 times the sine of 30, so that should be 170 newtons. Yes?
So the angle inside the smaller triangle will always be the same?
Always.
Okay.
Okay, so F parallel is 170 newtons. Okay, now, how many people looked at this and went, how am I supposed to find one of these forces if I can't figure out the net force? What is the net force in this question? Nope, that's the applied force. 0. This is the trick to this question. It's being pushed up the plane at a constant velocity. Thus, its acceleration is 0. And mass times acceleration is net force. Well, since the acceleration is 0, the net force is also 0. Okay, that's an important thing to know. Because now that also tells me that if I add all these forces up, I get 0. That means the force up the ramp and the forces down the ramp cancel. So I got 200 up, I got to have 200 down. I just calculated one of them to be 170, so the one I'm missing is 30. Okay? So anytime you see the word constant velocity, constant speed, or sits still, the acceleration is, and the net force is, right? And that makes your sum of all forces a little bit easier. Okay? Because now you know they all add up to 0. They're gonna cancel each other out in some way. Okay? So if I was actually drawing a true vector diagram of this, okay, I'd have FG, okay, I'd have normal force, okay, I'd have F parallel, force of friction, and then 200 newtons, and it would all go back to zero, right? My vector diagram would all go, eventually end up right back at the start. That sort of makes sense? We don't ever use these two forces. Once we found F parallel, then they're done. F parallel is the sum of those two forces, and I don't have to include them again. Okay? All right, so that's a trick. That's something we got to watch for. The words constant velocity are really, really important when we're doing a Newton's second law question, because it actually tells us this isn't a Newton's second law situation. It's a Newton's first law situation. It's the acceleration is zero. All right. Okay, try this one. Now we're sliding down the ramp. Okay, so still ramp, still inclined plane, still gonna get F parallel. Okay, give it a try. So if we're drawing the diagram of this, okay, so we have the 50 kilogram child. Okay. And she's on this 25-degree hill. Friction is resisting the sled she is on with a force of 150 newtons. Okay. We want to find her acceleration. So what force is pulling her down the ramp? F parallel, right? Okay. So I have to calculate F parallel then, okay? And that's always done the same way. I've got my FG here, which for this one will be 490.5 newtons, okay? And I've got my normal force, which I don't need to know the value of, okay? And then I've got my 25-degree angle, and here's F parallel. So F parallel will be the sine of 25 times 490.5. Okay, so 207.29 newtons. What can I find now? Got net. Yeah. Okay, I've got the force up the ramp, I've got the force down the ramp. Okay, I've already taken into account normal force and gravity. Okay, that's what F parallel is. So all I have to do to get F net is add those two forces together. F parallel, okay, plus the force of friction, understanding that F parallel is down the ramp and friction is up the ramp, so one of them has to be positive and one of them has to be negative. Okay. So I'm just going to go, that is 290, or sorry, not 290, 207.29 minus, okay, or plus negative 150. Okay, all right with that? So I should be left with 57.29, right? Newtons down the ramp. Can I calculate her acceleration now? Okay, goes right back. We're always doing these two steps, right? Did sum of all forces. That was all that work. Now I'm doing m times a, so 57.29 divided by 50 kilograms, just over 1.1. Oh, I got two decimals in there. All right, 1.1, yeah, 1.1, we only have two significant digits there, so 1.1 meters per second squared down the ramp. What if you wrote down? All right, down is straight down. This kid would be falling through the hill, okay? Not sliding down it. So down and down the ramp are different. I know that seems incredibly anal. It is, but it's also true. Okay, so just make sure you have down the ramp, up the ramp, not down and up, because those are different.
Should I like a sinkhole would work with how like the force pulling against it would be greater than what's resisting?
Yes. Okay, so when you have a sinkhole, the normal force is no longer able to counteract the force of gravity, and it usually has to do with something underneath, simply like a, a cavity that just can no longer hold up the weight above, right? All right, people kind of getting the whole inclined plane thing? I ask a lot of inclined plane questions. They're my favorite. Okay, so you'll see a lot of them, and it's because it makes you do a little bit of vectors. It makes you do a little bit of sum of all forces, m times a. They're a good type of question to make you do all the stuff basically from the beginning. Now we haven't talked about systems yet, and we're still going to get there. That'll kind of be tomorrow. Okay, systems are going to be Newton's second law questions with more than one mass. Okay, so it's still the same principles, it's just more than one mass involved. All right, we'll call it there.